We've spent time with formulas for converting expressions. You should always use true formulas only when rewriting expressions. You'll recall now two expressions appear in an equation. There's one on the left side of the equal sign and one on the right side of the equal sign. And one application of equations is word problems. Word problems or story problems can be frustrating at first, but they are in part an answer to the question, when are we ever going to use this? So to help, let's look at word problems in various settings. So last time we looked at taxes and discounts. Those are real life. But if we looked at too many different settings for word problems, and there are plenty possible, that may be overwhelming. So we're going to try to keep this controlled, and we're going to look at distance problems for the majority of this day. So the formula for distance problems, you may recall distance equals rate times time. And the thing is, most problems involving travel, right? So, distance equals rate times time. Most problems that use this formula, there's actually this really important detail. There are two journeys. Now, that might be two different people traveling. It might be one person having a first trip and a second trip, but if there are two journeys, it means that there are two distances and two rates and two times. That is extremely important for these problems. You have to apply this formula twice, once to each journey. Generally, it's not possible to just have a variable called d and just call it distance. Just saying, you create a variable called d and say, oh, what's that? That's distance. That's usually not enough because there's two distances in most of these problems. So instead, you have to be more specific. You have to say things like d is the distance traveled by the orange car, for example. So what do you do with the two distances? Well, that depends on the problem. So sometimes the two distances are equal. Sometimes the two distances add up to a number that's given in the question. What do you do with two times, right? So if there are two distances and two rates and two times, what do you do with the two times? That also depends on the problem. Sometimes the two times are equal. Sometimes the two times add up to a number given in the question. And on some occasion, sometimes one journey's time is obtained from the other by adding or maybe subtracting a number that is given in the question. So let's dig into an example. Two cyclists 66 miles apart start riding toward each other at the same time. One cycles twice as fast as the other. If they meet 3 hours later, how fast was the faster cyclist? So what are the two journeys? It's the two cyclists. There's cyclist number one and cyclist number two. One was faster than the other. Let's say we'll use capital D for the distance of the faster cyclist and then capital E for the distance of the slower cyclist. Are D and E both equal to 66? No, that wouldn't really make sense, right? If we did that, that means that each cyclist would cycle completely past the other cyclist when they met, and they would just each end up where the other person started. So we wouldn't say that D and E are both equal to 66. And then the next thing that people might think is, well, what if we just cut that 66 in half and just said D is 33 and E is 33? So each cyclist traveled half of the 66 miles. That's not really likely either. We shouldn't assume this anyway. That's an added assumption. It's more likely that the faster cyclists covered a bigger distance, right? Because look, they started at the same time. Back in the first sentence of the question, start riding toward each other at the same time, and then if they meet 3 hours later, they stop biking at the same time. They stop biking both at the moment they meet each other. So if they traveled the same amount of time, but one was traveling faster than the other, then the faster cyclist probably covered more distance than the slower cyclist did. So we shouldn't assume that D and E are both 66. That would be them biking past each other. We shouldn't assume that they cut this distance each in half and covered exactly half the distance each. That's an extra assumption that doesn't seem warranted. Instead, what we can say is that D plus E equals 66. That is, the amount of distance covered by the first cyclist added to the distance covered by the second cyclist equals 66. So neither of them traveled the full 66 or half of it, but whatever distance the first cyclist traveled is something less than 66, and then the second cyclist traveled another distance represented by E, and together, when we add those together, that's the entire 66 miles apart that they started. Let's have R represent the rate of the faster cyclist and S the rate of the slower cyclist. Then, because the second sentence in the question says one cycles twice as fast as the other, we can say R is equal to 2 times S. The times for both cyclists are the same, right? They start and end at the same time. They meet 3 hours later. So we'll just use T equals 3 for both journeys' times. So here's what we have. Then applying the distance formula to the faster cyclist's journey, we have d equals rt. If we apply the distance formula to the slower cyclist journey, we'll have e equals s times t. And just kind of collecting the other equations we have so far, we had already mentioned d plus e equals 66 and r equals 2 times s. Now, let's just summarize that information here in a table, and then the four equations are written right below the table. And take that equation d plus e equals 66, and let's solve for e by subtracting d on both sides. So we'll have e equals 66 minus d. Now, the second equation was e equals s times 3, and we can replace the e on the left side with 66 minus d, which we just did, right? So we'll have 66 minus d to replace the e on the left side, and the right side said s times 3. We'll just copy down s times 3. Now, note that if we take the equation that we just wrote, 66 minus d equals s times 3, we can replace d with r times 3 from the first equation. So now we'll have 66 minus r times 3 equals s times 3. And then finally, we can replace r with 2 times s. So we'll have 66 minus 2 times s times 3 equals s times 3. Simplify a little bit. 66 minus 6x equals 3s, and then add 6s to both sides, so you have 66 equals 9s when you have collected like terms on the right side. Divide both sides by 9. 66 over 9 equals s. Here's the thing. S, going back to the table, so we know really clearly what the variable means, because there's d's and e's and s's and r's, right? So s, there's 4 variables up here in the table. S represents the rate of the slower cyclist. If you go back to the original question, we were asked about the rate. How fast was the faster cyclist? We were asked about r. So now that we know s is the number 66 over 9, how can we get r from this? Well, take a look. R is equal to 2 times s. Right? We were asked for the speed of the faster cyclist. We called that r. R equals 2 times s. So we'll have r is equal to 2 times, and then replace s with 66 over 9. That is 132 over 9, and if we summarize this, the faster cyclist went 132 over 9 miles per hour. Here's an alternate method of doing this. So we introduced so many variables last time, and some people will prefer that approach, okay? There's something kind of clean about that approach. But if the number of variables is sort of not your taste, here's another approach to this is instead of introducing a variable e, let's just leave this question mark that's highlighted yellow there. The previous method introduced a variable to represent the slower cyclist's distance. Instead, let's just think about, again, how the two cyclists' distance need to add up to the number 66 provided in the problem. So d plus question mark equals 66. What does question mark have to be? Well, you can solve for question mark here by subtracting d on both sides. So that question mark should be 66 minus d. And so we'll just replace that in the table there. So we'll use d, the variable d, to represent the distance of the first cyclist, and then we'll write the expression 66 minus d for the distance of the second cyclist, because when you add d to 66 minus d, you get a total of 66. So we're still applying that principle that the distance of the two cyclists adds up to 66. So then with d equals r times 3, that's the distance formula applied to the faster cyclist, and then 66 minus d equals s times 3, that's the distance formula applied to the slower cyclist, and then our earlier equation, r is equal to 2 times s, the work actually at this point will look very much the same as we saw earlier, so we won't go through all of it. The key thing I'd like to point out, though, is that using either method, the formula distance equals rate times time was applied twice. Once for the faster cyclist, and once for the slower cyclist.